Welcome to 𝐓𝐴𝐻𝐻𝐿, the historic former home of the Royal Observatory.
And welcome to the original home of the Royal Observatory here in Greenwich.
In this programme, we'll be looking at the evolution of the telescope and how it's changed our understanding of the cosmos and our place within it.
And we'll be looking ahead to an event that will transform our view of the cosmos once more, the upcoming launch of the James Webb Space Telescope.
Welcome to the sky at night.
I have in my hand is a piece of technology that transformed the direction of Western science. It's a piece of glass ground into a lens. Now, with a lens came microscopes, but maybe more importantly, telescopes. The early telescopes looked like this. They had a very narrow field of view, didn't magnify all that much by modern standards, and were first taken up by the military. Seeing your enemy sooner was an obvious advantage. But soon, the curious turned their telescopes to the heavens. The first documented case of someone observing the moon with a telescope, surprisingly, wasn't Galileo. It was actually the Englishman, Thomas Harriot. This is a Harriot drawing of the moon. There are two reasons why we remember Galileo's drawings and not Harriot's. Firstly, Harriot's drawings weren't discovered until after he died. But secondly, Galileo was a much better artist. Before he was an astronomer, Galileo was an artist and a teacher of 3D drawing, so it's no surprise that his pictures were highly accomplished. But Galileo's interpretation of what he saw was his real triumph. With his 3D artistic eye, Galileo realised that what he could see on the moon's surface were actually geological features, craters, hills and valleys. The moon wasn't made out of magical moon stuff, but similar stuff to what we find here on Earth. The moon was just a small, rocky world. It changed our global view of things, and modern astronomy was born. In England, the arrival of the telescope was critical to the establishment of this place, the Royal Observatory. But for a nation on the rise, the fascination with the new technology was less about science and more about commerce.
The Royal Observatory was founded in 1675 to provide accurate star charts and catalogues to help improve navigation at sea. And this was a really hot topic at the time because merchants wanted to extend their trade routes for better profits, and governments wanted to extend their influence across the globe and get more taxes from that trade. So it was really important to invest in a new observatory.
So we're using the instrumentation for sort of navigation and commercial purposes, but why here in Greenwich?
Sure, it's a good question. Well, in the first instance, it's because it was free land, it was part of a royal park, so it was easily available. But as we can see, it's a great hilltop location, so we've got great views of the horizon. You can see the stars rising above the east and setting over in the west. And at that time in the 1670s, it would have been nice and rural. We're about 6 miles from St Paul's Cathedral, and we would have been surrounded by marshes and fields, so really good for observing.
It's hard to picture that now, because this is sort of the opposite of rural now.
Absolutely. If you fast forward 200 years to the Victorian period, this area would have been filled with factories, boatyards, breweries, all with huge chimneys belching out smoke and making it quite difficult to observe from this area.
And so a change was needed.
Absolutely. So the initial work of the observatory focused very much on mapping the heavens for navigation, but by the 19th century, new technologies were coming in, like photography and spectroscopy, and you needed much better observing conditions for that to get really good results. But unfortunately, the city was really starting to encroach on the observatory by that late 19th century, and it was the construction of Greenwich Power Station in 1910 that really brought matters to a head.
Oh, that one with the 4 chimneys?
The 4 brown chimneys, sure. So you've now got black smoke pouring out, you've got hot gases disrupting the atmosphere, you've got vibrations from the turbines disrupting your carefully calibrated instruments. Plus, to add to the mix, you've also got your electric railway line disrupting your magnetic measurements. So it really was time to consider a new location.
In 1946, a new site for the Royal Observatory was found in 𝐓𝐡𝐞 Castle, which sits under the cleanest, darkest, least electric skies in southern England. It's located 10 miles inland from Eastbourne, officially the middle of nowhere, East Sussex. The castle initially provided accommodation for the Royal Observatory's staff, whilst the Royal Observatory's observing would take place from a series of new domes designed by New Zealand-born architect Brian O'Rourke. O'Rourke had a background in the interior design of passenger ships in the 1930s, the golden age of the ocean liner. And you can see that coming out in some of the detail in the buildings behind me.
Building this place was a massive undertaking, and an impressive archive of the period is now cared for by Sandra Voss.
Oh wow, so these are the original plans, are they?
They are, yes. You've got Brian O'Rourke's name written in the corner there.
Oh yes,
yeah,
absolutely. When would the construction of the observatory start?
They did start building the observatory in 47 or thereabouts, and the locals weren't very happy when they saw what was happening to the to their beautiful castle, you know, the oldest brick-built building in the country. And so they said, oh, this is, you know, not in our backyard almost. So
right.
Then that's why they had to bring in Brian O'Rourke. So these are 1953. They had to rethink to make it as aesthetically pleasing as possible.
So was O'Rourke responsible for the copper?
I think so, and there's anecdotal evidence that they painted the copper with a mild acid
right.
that they thought initially was horse's urine, so that it went green very quickly. Of course, the majority of the colour is green around you, so it has to blend in with the countryside. So
which it does beautifully, doesn't it?
It does, absolutely
yes.
beautifully. You can't see it from a distance at all.
So when did the telescopes arrive?
I think they started pretty early on, but what they had to do, of course, build the domes first. So we've got some photos here. This is the main building starting to be built.
Right.
That's in 53. So you can see that the domes are taking shape now.
It's amazing to see that shape, actually, with just the framework before everything's gone on to cover it. It is just like a framework observatory, isn't it?
So steel framed and copper clad. And then, of course, they had to then have the domes built before they then started to crane in the bits of the telescopes. There's the mount coming in.
Through the slit of the dome?
Through the slit of the dome, the mount coming in there.
Wow.
And then this is part of the telescope in one of the domes as well, coming in. So, yeah, it's all...
That's incredible.
They're fantastic photographs, really fascinating.
I've been here many times in the dark, but I've noticed there are water features outside, and I've always wondered why they're there.
There is, yes. It's a beautiful lily pond, but who puts a lily pond in the middle of an observatory?
Have many astronomers actually fallen in?
Yes, they have.
Oh, right, okay. That's good to hear. So what was the purpose of the water?
Well, I think it was a filtration system and a reed bed system to begin with, but it's aesthetics as well, isn't it? I think it's all coming from, it's like the high walkways and the steps and making it look as nice as they possibly could. But yes, an ornamental pond is not exactly the best in an observatory, is it?
Water hazards aside, what O'Rourke achieved here is that rare thing, a technical facility which is also aesthetically pleasing. The brickwork, the bluey green of the gently corroding copper, and the reflections from the beautiful, if impractical, Italianate pond combine to give a feeling of being in the formal gardens of a grand house, rather than a place of cutting-edge scientific precision.
In total, there are 6 domes in the equatorial group, but without doubt, the most exciting element is to be found in Dome E. This is the 26-inch Thomson refractor, and it's absolutely huge. The eyepiece is right up there, so in order to look through it, I either need a high stepladder or I need to raise the floor. It's a testament to precision Victorian engineering that its 12 tons can be moved manually. In fact, it doesn't take much effort at all.
On top, you can see a smaller telescope. These days, it's a less powerful guiding scope, but it has an interesting history.
Since the 1820s, it was understood that irregularities in the orbit of Uranus were due to a hitherto undiscovered object nearby. In Cambridge, John Couch Adams had done the maths and worked out where that object should be in the sky. But it remained elusive, and it wasn't until 1846 that the planet Neptune was finally discovered. A triumph for astronomy. The problem was, it was a German triumph. And to make matters worse, it was a German triumph using bigger and better kit than we had in Britain.
Stung by the humiliation of ceding such a major discovery to a foreign power, the Astronomer Royal commissioned what was called at the time the Great Equatorial Telescope, the biggest bit of kit that Greenwich had ever seen.
But despite its impressive size, it never made any impressive discoveries. And all that remains of it today is a 12.8 centimetre lens, which is inside here, the understudy to the main scope.
In telescopes, bigger is better. But there's a problem. Because they are curved, the edges of the lenses act like triangular prisms, producing a rainbow from white light, so-called chromatic aberration. And that's not all.
The trouble with glass lenses is that the larger they get, the more prone they are to distort and crack under their own weight. The largest lens ever made is only 40 inches across.
It was Isaac Newton who first realized that because lenses are not the only thing that can provide magnification, a different type of telescope was possible.
Concave mirrors, like this one, do the same job as an equivalent convex lens. But in the case of a mirror, it can be much larger. Telescopes which use mirrors are called reflecting telescopes.
The 36-inch Yap telescope here in Dome B is a reflector.
Light enters the telescope and hits the primary mirror at the bottom. There it reflects and begins to focus, hitting the secondary mirror at the top, and in the case of this telescope, the light is bent back towards the primary mirror, which has got a hole in the centre, which lets that light through. And that's where you'd place your eyepiece or perhaps a camera plate to catch the light.
Using this design, the greater magnifications achievable provided astonishing breakthroughs. In the 1920s, on a hill just outside Los Angeles, the Hooker telescope, a reflector with a massive 100-inch diameter that's just over 2.5 meters, was being put through its paces by one Edwin Hubble. Hubble made two separate discoveries here at the Mount Wilson Observatory, each of them as revolutionary as Galileo's sketches of the moon. Both of them were made possible by the capabilities of a large reflecting telescope. The first thing he discovered was that some of the fuzzy patches of light some had assumed were nebulae made of gas were in fact something else entirely. Here's one such picture of those fuzzy patches of light, and Hubble's looking for individual stars, so he's labelled these as N for novae, these are exploding stars, but this one in the top corner turns out not to be a nova but a variable that comes and goes. And better than that, this isn't any old ordinary variable, this is a Cepheid. By recording a Cepheid's pulsation rate and its brightness, it's possible to calculate how far away it is. Not only was the fuzzy patch made of stars, Hubble found that they were outside our Milky Way. They had to be in another galaxy. Astronomers had been arguing for decades about whether there were galaxies out there beyond the Milky Way, but Hubble showing that those fuzzy patches of light were actually made of stars settled the matter once and for all. He also discovered something else. He found that these new galaxies seemed to be rushing away from us, and that the further away a galaxy is, the faster it seems to be receding. And it's that observation which gives us the idea of the Big Bang, a complete transformation in our understanding of how the universe began and how it's evolving, made by one man and a rather special telescope.
By the time the Royal Observatory had moved to 𝐓𝐡𝐞, it had done all it could to aid maritime navigation. So its mission became less astrometry and more astronomy itself.
In the 1960s, construction started on a new dome at 𝐓𝐡𝐞. It would house the biggest reflecting telescope Britain had ever seen. The 98-inch Isaac Newton telescope was inaugurated by Her Majesty the Queen in 1967.
In its time, the Isaac Newton telescope was one of the most powerful instruments of its kind in the world. And as a teenager, I was lucky enough to actually visit it. What I remember about approaching it was the fact that everything was beautifully maintained. These trees certainly weren't here.
These days, the structure of the dome is largely hidden by the forest that has grown up around it, but it's still an impressive sight to see.
Seeing that massive telescope up close for the first time, it really struck me. I was an amateur astronomer and I had an 8-inch reflecting telescope, and I couldn't help but wonder what that amazing 98-inch mirror could reveal of the night sky.
The Isaac Newton telescope was less powerful than the Hooker by just 2 inches, but newer, with better engineering, better control and more precision. And real results.
In 1971, Paul Murden and Louise Webster observed a star which was behaving oddly. They could see the star and they knew it was in a binary system with an orbit of 5.6 days, but they couldn't see the companion. It was nothing at all. They wrote up their report and published it in Nature, and they concluded that this could be a black hole. And they turned out to be right. And that's quite something, because they provided the first tangible evidence of something which up until that point had only been theorized.
But despite its successes, the writing was on the wall for the Isaac Newton telescope. Its last observation here was in 1979, the victim in part of the British climate. When the Queen came to open the telescope, the plan was to use it to show her magnificent live images of Saturn. But on the day, it rained. In the end, however, it was all about money.
A combination of funding cuts and a more international approach to cutting-edge astronomy meant that Britain couldn't have her cake and eat it. A choice was made, and 𝐓𝐡𝐴 lost out.
What was left of the Royal Observatory's staff moved to Cambridge, and the better telescopes dismantled and moved abroad. The institution itself staggered on for a few years before being dissolved completely in 1998. Its funding diverted to pay for Britain's involvement in international collaborations.
Astronomy today is fiercely collaborative. UK astronomers helped to build and then use the telescopes of the European Southern Observatory in Chile. We also have access to telescopes in Hawaii, and of course the good old Isaac Newton telescope and its larger sibling, the William Herschel telescope on La Palma in the Canary Islands.
The Bepi-Colombo spacecraft, currently en route to Mercury, is another international collaboration involving British scientists. It's recently sent back its first stunning pictures of the planet. There'll be more on this in next month's programme, but in the meantime, if you'd like to have a look at Mercury for yourself, you're in luck. It's currently visible in the morning sky just before sunrise.
Now, I normally do this part of the show from my back garden in Leicestershire, but as I'm in 𝐓𝐡𝐴, and surrounded by lots of telescopes, it would seem rude not to use them. Okay, well, the noise you can hear is the drive on the telescope, so it's currently tracking everything up there in the sky as the Earth rotates. And what we're hoping to do is to get a live view of Jupiter using a digital camera which is fitted on the end of this 10-inch refracting telescope. It's the first time a digital camera has been attached to one of the telescopes here at 𝐓𝐴. Quite exciting. Okay, so here we've got our live view of Jupiter. You can just about make out the two main belts running parallel to the planet's equator. The planet also looks slightly squished, as it does because it's a very fast rotating planet. But you can also make out the moon here as well, and that's Europa, quite close to Jupiter. It's wobbling about a bit because it's live and we're looking at it through Earth's atmosphere. And because from the UK Jupiter's quite low down, that sort of blurs our view of it at the moment, but it will get better over the years to come. But it's fantastic to be able to see a planet live on the screen here through this amazing 10-inch refracting telescope. And here's a wonderful photograph of Saturn. Now, I didn't take this. This was taken by John Fox, who's one of the volunteers here, who actually rigged up the digital camera on the back of this telescope. But it's a beautiful view of the planet. You can see just about make out the little division in the rings there, which is known as the Cassini division. And the rings stand out really well at the moment. Now, Jupiter and Saturn are easy to see during November. If you go out just as the sky gets dark, then look towards the southern part of the sky, you should be able to see a bright star-like object. That's Jupiter. And then look to the right of it and slightly lower, that's Saturn. Dimmer than Jupiter, but still brighter than any of the other stars around it. Now, there's a lovely moon shining away out there this evening as well, which is a good reminder that there's an important event coming up in the middle of November. On the morning of the 19th, there's what I would describe as a tricky partial eclipse of the moon. And it's tricky because it occurs just before the moon sets. It favours those who live further north and west in the UK. So if, for example, you're in Stornoway, you get about an hour of partial eclipse before the moon sets. But from London, you'll just get a few minutes before the moon disappears below the horizon.
Progress in astronomy is inextricably linked to technology. The production of high-quality glass was exploited to make lenses for the first telescopes. The idea of using mirrors rather than lenses meant that large reflecting telescopes could be made, allowing astronomers to see much further into space.
And of course, the next big leap in technology-driven progress was thanks to spacecraft. The Hubble Space Telescope, for instance, has been wowing us with amazing images for over 30 years. My favourite by far is the Hubble Deep Field, which really showed us our insignificant place within the universe.
The next grand space telescope project is the much-anticipated James Webb Space Telescope, due to launch in December. Chris talked to Paul Eccleston, the lead engineer of its MIRI instrument, made here in the UK.
Well, thanks for coming to see us. In all the history of telescopes, there's never been one that looked like this.
Yes, it has this massive sun shield that's going to protect it from any stray light from the sun and the Earth. And that's also going to allow us to get the telescope really cold because it's operating in the infrared.
So that's the mirror sitting on top there?
Yeah, so at the top here you see the primary mirror, which collects all the light. It's got a massive collecting area that's something like 20 times the size of the Hubble telescope. That then reflects the light back to where this secondary mirror deploys out here, comes back in through the middle missing segment, and then into the instrument module behind, which is where the cameras are housed. And we make sure that the primary mirror is exactly the right size and shape by actuating each one of these 18 segments individually.
Oh, so they can move on their own?
Yeah, so each of those has got 7 degrees of freedom. We can move it around in all directions, and we can tip and tilt it, and we can even change the focus of each segment individually to get the perfect image. It's one of the lessons that was learnt from Hubble to make sure that that's all adjustable once we're in orbit.
Oh, because Hubble's mirror was slightly the wrong shape. How precise do you have to be when you're lining these segments up?
So the total surface for that primary mirror has to be a small fraction of a human hair thickness from the nominal shape. It really is extremely precise.
So tell us about the instruments on board, and particularly MIRI, which I know you've been involved in.
Yes. So in here we have 4 different instruments. There's 2 cameras that are working in the near infrared. Then we have a near infrared spectrometer, NIRSpec, that was built out in Germany. And then finally the MIRI instrument, that's the mid-infrared imager and spectrometer that was built and assembled by a team from around Europe and the US and assembled here in the UK.
What were the biggest challenges, particularly with MIRI?
So for the instrument, the biggest challenge is how cold it has to be. We operate down at 6 Kelvin, so even colder than the rest of the spacecraft, because it needs to be as cold as it possibly can be to get the detectors as sensitive as they need to be to see those very early galaxies in the universe.
And this is why that sensitivity, that desire to be cold, is also why the spacecraft's going to where it's going. It's not in orbit around the Earth like Hubble is.
No, it's not. So it's going out to well beyond the orbit of the Moon, a place called the 𝐷2 Lagrange point, 1.5 million kilometres away. If it was in orbit around the Earth, you'd never be able to get anywhere near as cold as we need to.
Great. Well, we'll be watching with you and the rest of the team as it launches, and then keeping everything crossed for the first images and data. When should we expect the first images from the telescope?
So once we launch, there's about a 6-month period during which we're transiting out to the Lagrange point, and we're unfolding everything, we're aligning the mirror, and we're cooling down because we've got to get rid of the heat that we take up with us. So it's going to be approximately 6 months before there's any data visible, and then after that, data will then start flowing a further 6 months into the mission.
Great. Well, we'll look forward to it, and we'll come and talk to you when it's all a success.
Super.
Thanks
you very
so much.
The James Webb Space Telescope marks the latest steps in our astronomical journey, but they won't be the last. Even as we speak, in the Atacama Desert in Chile, we're building the ELT, the Extremely Large Telescope.
Enhanced by computer-controlled adaptive optics, the Extremely Large Telescope will have a mirror 42 meters in diameter. That's 5 times larger than the largest telescopes operating today. To give some context, people who are building the ELT's dome usually build sports stadia.
It's really hard to know where we go from there, but history gives me the confidence that we'll find a new technology that will enable us to look even further out there.
That's all for this programme, but do join us next month when we'll be looking back at the best bits of the sky at night in 2021.
Until then, from 𝐓𝐡𝐞
And from the Royal Observatory Greenwich, good
night.
night.
From black holes to the Big Bang, Brian Cox takes us right to the face of the sheer drama that changed the cosmos. Universe is streaming now on iPlayer. And you can listen to the Universe soundtrack featuring Foals and Hans Zimmer on the BBC Sounds app.